Hi, I'm presenting Learning Graph Embeddings for Composition Zero-Shot Learning. I am Farjad, and this work was done at the University of Tübingen with my amazing collaborators. In Composition Zero-Shot Learning, we are tasked with learning state-object compositionality. We make the assumption that at training time, we can observe all objects with some states and all states with some objects. And at test time, we are tasked with generalizing to novel compositions of them. Towards this, some previous methods have aimed to learn state and object separately and transforming the output, and a second line of work focuses on learning a joint compatibility function for state-object compositionality. Our method is more closely related to this line of work. We formulate this problem as a mapping from the image domain X by a learnable function f, and a mapping from the semantic space of visual primitives by a learnable function g. Dot product signifies their compatibility. Our key contributions are: we propose a novel graph which can be created independent of an external knowledge base. Using this graph, we propose a method that achieves state-of-the-art performance on all benchmarks, and we also introduce a new benchmark task that addresses the limitations of the field. Our graph consists of state, objects, and their compositions. The key intuition here is that every composition label signifies three connections in the graph: a connection between state and object, and a connection between state and object to their compositions. Connecting all these nodes, we enforce a dependency structure within the network, and this leads to knowledge sharing between seen and unseen composition. So for example, when we're learning a cute dog, the model is aware that I will later on see an old dog through this connection dog, and this leads to regularization of the model. We initialize this graph with word embedding model and feed this through a GCN. On the output representation, we use the composition nodes as the classifier weights. With our compatibility function, we optimize across entropy loss over the training compositions, and at test time, we do an inference over the full composition label space, leading to generalized zero-shot performance. We also introduce a new benchmark called Compositional GQA. This dataset is curated from the GQA dataset and contains 870 objects and 453 states. With a composition label space of 9,300, this is the most comprehensive benchmark for this task. Results on MIT-States on generalized zero-shot performance, we see that the previous state-of-the-art SimNet achieves an AUC of 3.0. CGE, our method, achieves an AUC of 6.5, and this is double the improvement. On base class and zero-shot performance, also known as the best seen and unseen accuracy, we again see a major increase in performance. And towards accuracy on state and objects, also known as visual primitives, we again see that the model has a major improvement. Since we do train our model end-to-end, we also include a simplification called CGE fixed feature. This freezes the resonant backbone and only trains the composition network. We see that all of our observations still hold. And another observation we make is that while SimNet uses an independent object classifier, our fully composition network is also a better object classifier. Moving on to UT-Zappos, we see that all of our observations still hold, whereas CGE consistently outperform all the baselines on all the metrics. On the new benchmark CGQA, the first observation we make is that due to its large label space, it is significantly harder than the earlier two datasets. And while our model CGE still achieves state-of-the-art performance and doubles the AUC of the closest baseline. Ablating over the graph, if we directly use word embeddings with our cross-entropy framework, we already achieve state-of-the-art performance. Introducing a graph from a state and objects to their compositions, we achieve an AUC of 7.6. Introducing a latent representation on composition, this improves to 8.1. And using all of the connections in CGE, which also connect state and objects, we achieve an AUC of 8.6. On qualitatives, we show an example where the top prediction matches the label and an example where the top prediction does not match the label. We see that usually the top three outputs of the model contain the correct visual output, but the label only contains one composition. This is a limitation that future methods need to focus on. Retrieving images from a seen composition to an unseen composition, we see that the top image retrievals are all semantically correct. Thank you for your attention. Our code is open source, and you can attend our poster session for further information. Thank you.